These are the first day of the notes for 4.2. I would suggest you have a color, like a colored pencil or a red pen or something, because your notes are in black and white, so the shading's kind of grayish. But we are going to be finding, it seems weird that we're going from all this integrating and anti-derivating and moving into finding the area under a curve, which seems like it's just a huge mutually exclusive topics, but they're actually very connected. We are going to work with area under a curve for several days, and then we're going to tie integration into it. One of calculus's biggest claims to fame is that it can deal with curvature. In particular, we can find the area of things that aren't rigid and or aren't circular. Up until now, your formulas are basically for polygons and parallelograms and triangles and rigid-sided things, unless you're working with a circle. We know that the area of that is pi r squared, but then it bodes the question of why is the area of a circle pi r squared? That actually comes from calculus and an integration process. So although it seems like, why are we integrating? The process of integration gives us all of our higher formulas, even in geometry. It gives us formula for surface area and volumes of all those solids that you did in geometry. So we're just going to, for a while here, not tie it into integration yet. We are going to do what we call the area problem. And the area problem is to integration as the tangent line problem was to derivatives. Remember, when we first started dealing with derivatives, we were talking about the slopes of the tangent line. And when we start dealing with integrals, we're actually finding area. And so you don't get the connection yet, but eventually you will. So to start off, we're going to have a function that we're going to call f of x. And in this case, my f of x, I'm going to go point at the curve, as should you. F of x is x squared plus 1. It's a parabola opening up from 0, 1. And I'm not going to be able to get that exact area yet, but we're going to start doing some approximations of area today. The first thing we're going to do is we are going to chop this into some rectangles because we know how to get the area of a rectangle. So we're going to go from 0 to 2, and we are going to chop it into 4 rectangles. So we'd say n is equal to 4. So if I'm going from 0 to 2, which is a distance of 2, and I chop it into 4 rectangles, then I know the bottom of each rectangle, which we call delta x, has to be equal to a half. It's just saying there's 4 halves. So each one of these is a half, a half, a half, and a half. And in a formula, we would call that delta x. But really, it's the base of all of those rectangles up there. And you might say, well, you don't have rectangles. I'm going to go make them right now. So what we're going to do is we're going to go up, hit on the right side, go over, and go down. Then I'm going to go up again, hit on the right side, make a big dot, go over and go down. Hit on the right side, over and down. And then lastly, hit on the right side and just go over and down. So for the rectangles I chose to draw right here, all of them hit the curve on the right side. So we know that the base of every rectangle is a half because we were told to make 4 of them spanning from 0 to 2. And there's a formula for that, but it's just common sense. If you have to make 4 rectangles in a distance of 2, they're each going to have a length of a half on the bottom. So we know the bottoms of all our rectangles are 1/2, 1/2, 1/2. Well, we could find the area of all these rectangles if we could then get their heights. But you'll notice that their height, since I drew them so the right side always hits on the curve, their heights are the y values at each of those dots, or the f of x at each of those 4 places. So we really say that the height for the way I drew the rectangles is really just going to be f of x, and they call it f of x sub I for the first, the second, the third, the fourth rectangle. Well, it seems kind of weird. Let's go actually do it on the next page. So I drew it out nicer on this page, and you can see that I am going to be estimating the area under the curve by finding the area of the green stuff in the rectangles, and it's going to be a really poor estimate, and it's going to be way over because there's so much green stuff above the curve, but we'll accommodate that later. So right now we're going to find the area of these 4 rectangles. We're going to call them area 1, area 2, area 3, area 4. Sometimes that's called A sub I, and it just stands for the ith rectangle, the first, the second, the third, and the fourth. Well, each one of these has a base of that delta x. In this case, it was a half. So every one of my rectangles, when I do base times height, I'm really doing that delta x, which is a half, a half, a half, a half, times the height of the rectangle, which is where does it hit it up on this curve. For instance, for this one right here, for A, let's do the area of rectangle 2. I would do its base, which is a half, times its height. Well, right here, sorry, I'm trying to draw in blue. Right here, to get the height of the rectangle, this is at the point 1 comma f of 1. And f of 1 is, remember that curve is x squared plus 1. So f of 1 would just be that point on the curve, which would be 1 squared plus 1, or 2. So the height of this rectangle right here is 2. And I'd say the area of that second rectangle is a half. It's just area of rectangles, base times height. It's just that the height is going to be some spot on the curve, and the base is going to be this change in the x-axis. So let's go do the area of the entire region, which I'm calling A sub r. What I'd have to do if I were to write a formula for it is add up, that's what this means, all of the delta x's, which is all of the bases, times all of the heights. This is just fancy notation for, hey, add up 4 rectangles. So what I would do is I'd take each rectangle and I would do its base times its height. And for all of these, the base is a half. So I'm going to do 1/2 times, right here, the height is, that's at the point 1/2 comma, f of a half. Well, what was f of a half? F of x is x squared plus 1. So it'd be 1/4 plus 1, or 5/4. That would be the area of rectangle number 1. Plus, then I'd go get the area of rectangle number 2. It also has a base of a half, but its height is going to be 1 squared plus 1, or 2. Then I'm going to go find rectangle number 3's area. It has a base of a half, and its height is going to be at f of 1/2, or 3/2. So I do 3/2 squared plus 1, which would be 9/4 plus 1, which is 13/4. And you can use your calculator if need be. This one's pretty doable without one, but I will show you how to use it on some of the more intricate functions. Last, I need to get the area of this last rectangle. And it is, again, having a base of a half, but its height is all the way up to here on the right-hand side of the curve. This whole thing is the height of the 4th rectangle. Well, that's at the point 2 comma f of 2. And f of 2 is x squared plus 1. So it's just 1/2 times 5. And if you went and did that all on your calculator, the easiest thing to do, because these all have a base of a half, the easiest thing to do on your calculator is pull the half out and then just do 5/4, or 1.25, plus 2, plus 13/4, or 3.25, if you want to do decimal, plus 5. And if you do that on your calculator, a 5.75 comes up. So is that an overestimate or an underestimate? And the answer is it is a grossly overestimate. You could see that there was so much green stuff above the curve. And why? Because the rectangles extended over the curve. What caused that mathematically we'll discuss on the next page. All right, so now I'm going to divide this differently. I'm going to divide this so I get an underestimate. I'm still going to make 4 rectangles. So I'm still going to take 4 rectangles and span 2 on the x-axis. So I still have that delta x being a half. But I'm going to go up here and hit on the left side of the curve this time. So I'm going to go up and hit on the left. I'm going to go up and hit on the left. I'm going to go up and hit on the left. And I'm going to go up and hit on the left. And I will never hit the curve over here at 2. So basically now when I'm hitting on the left, I'm going to deal with these 4 x values that give me the height. Well, let's go to the next page where I have it laid out nicer. It's the same picture, and we call this a left, I'm going to write that on here, a left rectangular approximation method, also known as an LRAM. It stands for left rectangular approximation method. The one I did previously would have been known as a right rectangular approximation method because I was hitting on the right. On this one, I'm hitting the curve at all the left endpoints of the rectangle. Notice this one does not get used. So what I'm going to do is find the area of 1, 2, 3, 4 rectangles. And I've got the work for that down here. All of them have a base of a half, but their heights, now the first one has a height at f of 0. F of 0 is 1. Because again, remember, this is the curve f of x, which is x squared plus 1. So right here, this would be at the point 0, 1. This would be at the point 1/2, and we already said that was at 5/4 or 1.25 if you prefer a decimal. This would be at the point 1, 2, and this one would be at the point 1.5, and we had 13/4. Notice I am not using this one at all because I don't hit over there. So if you do that, and just go to your calculator, you get 3.75. And again, I'm getting an underestimate. You can see it. This green stuff is missing all this, so it doesn't give me a very good approximation for the area under the curve. It doesn't mean, though, that an LRAM is always an underestimate. I can draw a function where, let's go like this, where if I do a left endpoint, I'm going to go grab a red, head over, hit on the left, hit over on the left, hit over on the left. Now I'd have an overestimate because I would be extending above the curve. So this is a good way to remember it. It has to do with whether the function is increasing or decreasing. If the function is increasing, a right rectangular approximation gives you an overestimate, like on the previous page. And a left on an increasing function gives you an underestimate, like right here. The way you can kind of remember that is just remember this acronym spells RIO. Or just look at it, like sketch it out. And if you're like, okay, my function is going like this, and I need to know if my right endpoint gave me an over or an underestimate. Go over and hit on the right, go over, hit on the right, up and over, hit on the right, up and over, hit on the right. And you'll see that your right on a decreasing function is an underestimate, because again, I'm missing pieces of the curve, of the area, I mean. So, and then consequently a left on a decreasing is an overestimate, just like up here. So if you can remember RIO, the other 4 fall out naturally. All right, so those weren't very good estimates. I had a lot over the curve in the first one with the RRAM and a lot under the curve with the second one with the LRAM. So how could I be more accurate? How about if I hit in the middle? So how about if I head right in the middle of the interval, hit the curve, and then draw a rectangle? And then I go up and I hit in the middle, hit the curve, go up and over, and draw a rectangle. You'll notice this seems to be balancing much better the amount of area that's in and outside of the curve. So I'm going to go up, hit in the middle. So this seems to be balancing. I'm missing this, but I'm gaining this in my rectangle. I'm missing this on the curve. They kind of seem in balance. It looks like I'm going to have a much better estimate with these midpoint rectangles. And we call this a MRAM for midpoint or middle rectangular approximation method. Well, again, what would my area be? And again, I'm approximating the green stuff by finding the areas of the rectangles. Well, they still all have the same base. They all have a base that I'm going to use of a half. When I do base times height on each of these, I will be using a half. Let's go to the next page where I have it drawn out nicer. So this is identical to what we just did. So when I calculate the area, I have 1, I have 2, I have 3, I have 4 rectangles that I am going to add up. It'll give me the area of the green stuff, which is an approximation for the area under the curve. Let's see how good it gets. I'm going to do the area of the entire region is rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4. Each rectangle is base times height. Each rectangle has a base of a half. So let's go look at rectangle number 1. Its base is at a half. Its height now is hitting in the middle here. So that would be f of, in the middle would be 0.25. So I would use the middle value of the base. That would give me area of rectangle number 1. Area of rectangle number 2, so back to the picture, also has a base of a half, but now I'd be hitting the curve in the middle. So this is the point right in the middle of these, 0.75, comma, f of 0.75. So I'm going to just write f of 0.75. Plus, again, rectangle number 3, this is hitting in the middle at 1.25. And then plus rectangle number 4, that would be at 1.75 that it's hitting the curve. So the height of that rectangle would be right here at f of 1.75. And this is where I'd like you to take your calculator out because I'm going to show you a slick way to take care of that on your calculator. So take out a calculator. I've got one logged back here. And a good way to deal with the decimals and stuff quickly is to go enter your curve under your y1. We are dealing with the curve x squared. Again, I didn't use the calculator for the other two because I could plug stuff into x squared and add 1 to it without wasting my time on a calculator. But when I'm plugging in those decimals like 1.75, I don't want to do all those by hand. So what I do is I go enter it in y1. I'm going to go to table set, and if it isn't already, you're going to go down and you're going to set it over to ask and hit enter so that when you create the table, it can be tailor-made to whatever you would like it to be. So now when you go to your table, you are allowed to enter the values that you would like. So if you can kind of take a look, I want f of 0.25. So in my table, I'm going to do 0.25, 0.75, 1.25, and 1.75. And those specifically, that's where if you set it to ask, it's kind of nice. So I want to ask it what the height would be at 0.25. I'll hit enter. And then I'm in the middle of a half and 1, so I'm at 0.75. For my next, f of that would be 1.5625. And then my next one was f of 1.25. And then my last one was at 1.75. So when I use that to help me find the area, keep in mind, here's all my f ofs at those middle spots on the graph. So I'm going to leave that up there. What the easiest thing to do on your calculator is to take this half, pull it out front, and then you'd have f of 0.25, which was 1.065, plus f of 0.75, which is right there, 1 point. So let your calculator table help you for the ones that you prefer not to do by hand. And then this would be 2.5625, and then this would be 4.0625. And if you did that on your calculator, go ahead and write it down. I'm not sure what it is, and I don't want to go type it all in. I probably should, but I don't want to. So I'm going to kind of estimate it. You're at about 1 plus about 1.5 and 2.5, 2 and a 1/2, so that would be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, about half of 9. It's going to be about 4.5-ish just by estimating. You go do it exactly though. So it says for comparison's sake, the exact area is actually 4.666 under the curve. You might say, how does anybody know that? And the answer to the question is you get it actually with integration later. We're just doing estimates today. We had a gross overestimate with our RRAM. We had 5.75. And then we had an underestimate with our LRAM. I believe that ended up being 3.25. But we're pretty close when we did the midpoints. This ends up being like, I think like 4.5-ish. You can wrap that up. And then that bodes the question, well, okay, how could I get even closer? So I had a overestimate, an underestimate. The midpoint was better. But how about if I want to get even better and better? And the answer to that is you make more rectangles. Not only just more, if you could make an infinite amount of them, and they're infinitely thin, so your delta x actually approaches 0, so that you're making just an infinite amount of these tiny, I'm making little rectangles in here, you'll be really close to the area under that curve. You won't miss much or overestimate much. And I would tell you that as you do an infinite amount of them, you actually get the exact area. Now, would I ever make you do an infinite amount? No. So we're going to practice on the worksheet the process of estimating using LRAM, RRAM, and MRAM. So if you could take out your worksheet, we are going to do the first one on the chart together. So you'll need a blank sheet of paper. You might want to pause this video and get a blank sheet of paper out. You're going to do 5 problems. I didn't label the chart, but this is problem number 1. It's the function x squared plus x. I'm going to be looking at it from 0 to 4. I'm going to use a left rectangular approximation method. And you might say, where's she getting this from? It's from the worksheet number 1, where it says Riemann sums. I'm going to use a change of x, I was actually told, of 1, and my answer, according to the chart, is supposed to be 20. So I'm going to show you all the work you need to show with this one. You'll need a calculator out, not for this one, but for a couple of the other ones you might want to take advantage of your table. This one won't be difficult at all to do without a table. So first thing you're going to do is you're going to provide me with a sketch. Look at the 4 bullets up on the top. It says first thing you need to do is sketch the curve on the given interval. So I'm going to go sketch x squared plus x, and that's what my function is, on the interval from 0 to 4. And you can use your calculator to help you sketch it if you would like. It's a very steeply inclined parabola that opens up. Then you're going to drop this down. You're going to lightly shade that in. I'm going to go grab a highlighter. You can just lightly shade it with your pencil. I'm going to grab a highlighter. I'm going to shade that in lightly. So I'm going to use an LRAM, left rectangular approximation method, to estimate the area under this curve. So the first thing I need to do is, because my delta x is 1, I need to make 4 rectangles, but I start on the left. So what you do is your first dot hits the curve on the left, and then you go over to the next one. Notice I didn't provide me with any area. Then I go up, hit it on the left, and I go over. I go up, hit it on the left, I go over. I go up, hit it on the left, and I go over. Again, had that said right approximation method, I'd start here, go over, hit on the right, and I go down. So if it says left, start on the left, hit the curve, and head on over. So on each one of these, my delta x, or the base of each rectangle, is 1. I have A1 is actually not, there's no rectangle there, A2, A3, and A4. So I am supposed to divide it into the rectangles, which I did. I've got 4 of them because it said delta x is 1. So my rectangles would be 4 minus 0, the length of the interval. And I am having a delta x of 1, so I'm going to have 4 rectangles, which makes sense. All right, so I need to shade them all in, label them A sub I, which I did. I've got A sub 1, A sub 2, and now I'm going to show my work. My area of the entire region will be area of rectangle 1 plus area of rectangle 2, area of rectangle 3, area of rectangle 4. Each rectangle has a base of 1 or a delta x of 1. So this is going to be 1 times the height of that first rectangle, which is 0, because that's f of 0 is 0. So if you put in a 0 here, I'm up at 0. That's this dot right here. The height of my next rectangle right up to here is at f of 1. So I'm going to have 1 times base times f of 1. Well, where is that? It's 1 squared plus 1, which is at 2. So that's going to be at the point 1 comma 2. Plus, rectangle number 3 hits up here at 2 comma 2 squared plus 2, which is 6. So base times height. And again, base times height. It's 1 times 6 for that third rectangle. And the last rectangle has a base, again, of 1, and its height is over here again on the left, because I'm doing an LRAM, at f of 3, which is 3 squared plus 3, or 12. So when I add this all up, normally I'd pull the common delta x, or the common base, out front, but it's just a 1, so I guess it doesn't really matter, but I'm going to show it in all its detail. I add that up and I get the 20 that I'm supposed to get. Now, before you go work on this, what would the difference have been if I had said a right rectangular approximation method? Well, you would have gone up and hit on the right, gone up and hit on the right, up and hit on the right, up and hit on the right, and then you wouldn't have ever used f of 0. So your bases would have all been the same. They would have all been 1, but now you would have been using the right sides of the rectangles for their heights. So I hope that's enough help for you. I did an example like number 2 on the back, so you can see it. And that should help you out. You have 4 to do on your own. Go ahead and again use your calculator for any that get 2 decimally, and you have a good one.